Okay, so the organizers asked us to present an opinion style talk, and so I will tell you what that opinion is. But first, I just want to explain the bigger picture and how I arrived at the topic of learning in the first place. So I'm interested in how we extract meaning from the world and share that meaning with others. So my focus is on semantic learning and memory. And specifically, the big question for me is, how is it that we use concepts so flexibly? And how are they represented such that this flexibility is possible? And what I mean by flexible is that concepts can activate different information in different contexts. So we can use one word or one concept to cover an impressive range of meanings. So then another question is, how do we get to that point? What do we learn about concepts that lets us use them in this flexible way? And so I will talk about all of these things in more detail, but for now I will go ahead and summarize the main argument, which refers to the what, why, and how of concept structure learning. Okay, so what is it that we learn when we learn about concepts? I argue that what we learn is a feature-based structure for each concept that captures the feature co-occurrence statistics across instances of that concept, or the feature distributions within the concept or category. And why do we learn this feature-based structure? Because it has the potential to explain the ways in which concepts are used flexibly in language and thought. And then finally, how do we learn this feature-based structure? I argue that we learn a concept's feature-based structure within a distributed representational system. And distributed itself can mean different things in different contexts. So just to clarify what I mean here, I use distributed to mean to reflect the situation in which an individual neuron or unit represents many kinds of information, and representations emerge of patterns of activity across a larger set of these units. And this is the kind of representation that is crucial for neural network models, deep network models, and so on. Okay, so to flesh out these ideas, I will first start with the why. So why might we want to learn a structured representation in the first place? And again, this refers to the very interesting and complex phenomena in which a single concept appears to have different meanings in different contexts. And so one of the more obvious examples of this is figurative language or metaphors. So if I tell you that the train is a worm, you're able to generate some images of what this means. You can conjure up an image of what it looks like. So maybe you imagine a long train weaving between hills. And so when you do this, you're activating some information from the worm concept, even though an actual worm is not present in your interpretation. And some work has suggested that the interpretation of metaphors, at least in part, can be explained by the activation of relevant features and the suppression of irrelevant features. And this is what I found in this paper with Sharon Thompson-Schill. So when you interpret the metaphor, the train is a worm, you might activate a worm's elongated shape and how it slithers, but you suppress the information about its sliminess or its smallness. So this is reflected in property verification reaction times. So after you read the metaphor, it's harder to verify that worms are slimy than it is to verify that worms slither. And as it turns out, the response of the left inferior frontal gyrus, or LIFG, during metaphor comprehension relates to the extent to which these features are activated or suppressed. So here we can see that individual semantic features, such as elongated, small, slimy, and slithers, these individual features are potentially important in understanding how we use concepts flexibly. But figurative language isn't the only situation where we see the flexibility of conceptual meaning. So this is seen to some degree in all language use. So even when simple words are combined in literal ways, features are flexibly activated based on context. So think about, as an example, think about how the word dark has different influences across different kinds of nouns. So for example, a dark diamond may be slightly darker than a regular diamond, but dark paint could in theory be as dark as anything could possibly get. So somehow our brain is flexibly adjusting the level of darkness in these context-dependent ways. And so in this paper, we found that the degree to which the semantic features are modulated when two concepts combine is predicted by feature uncertainty. And so here, this is the brightness uncertainty of each concept, and that's shown on the x-axis. And on the y-axis is showing the degree to which this feature is flexibly modulated in these different contexts. And again, what we found is that the LIFG contributes to this process because it is sensitive to the degree of feature uncertainty when people read these combinations. But the takeaway from this study I want to highlight here is, again, It's highlighting the relevance of individual semantic features in understanding flexible concept use. And it also reveals how these flexible conceptual processes influence neural activity. Okay, so semantic features are so important for conceptual flexibility. How are they represented within a concept to make this flexibility possible? So any representation or model of concepts should be able to explain the relevant phenomena. So in our case, we need a concept model that incorporates the importance of semantic features, but also has the potential to support flexible concept use. And the idea that I've been working with is to model individual concepts as feature-based network structures that capture clusters of feature co-occurrences or the statistical distribution of features within a concept or a category. And so on the left is a schematic of this network. You can think of this as a graphical network. Here, the nodes represent individual semantic features like elongated, slimy, slithers, and small. And the edges represent the extent to which those features co-occur across instances of a concept. And the right is an example of a real-world concept network for the concept chocolate. And so here you can see that the real-world networks are slightly more complex than the schematic version, but it's still the same thing. So you still have the nodes as representing the individual semantic features and the edges capturing the co-occurrence statistics for each pair of features. And what we found in this paper is that the topologies of these networks or different aspects of network structure potentially relate to how concepts are flexibly used. So specifically, concepts that have a strong core periphery structure, and this means that they have one densely connected set of features and then a more weakly connected periphery. So these concepts correspond to words with higher semantic diversity, meaning that the words are used in more diverse contexts in language. So this is some promising initial evidence that these concept network structures can be used to understand flexible concept use. Okay, so if this is the kind of structure that we learn, then how do we learn it? So the last part of this argument is that we learn these concept structures within a distributed representational system. But first I want to take a step back and discuss the approach we took to explore this question. And I will go into more detail for this study because this is the study that is directly about learning. So our approach here was twofold. So first, we wanted to know what humans can learn. So in our case, we want to know what information humans acquire during concept structure learning. But we also want to know if there are any specific characteristics in how or what humans learn, because this will give us more of a foothold to compare different models against human behavior. And once we have the human data, we want to test a set of computational models on the same learning tasks. And so here we do want to know what the models can learn, but we also want to know if the models reflect the same specific characteristics we observe in human learning. So we don't just want a model that performs the best overall, but we want a model that behaves the most similarly to humans, because this will give us insight into what mechanisms or representations might support human learning. Okay, so now I will dive into the details of this concept of category structure learning study with Anna Shapiro. So the broad questions we had going into this study were, what can people learn about category structure on relatively short timescales? And how do the specifics of a category structure affect learning? What we did is we manipulated each category's feature-based structure. So we have these two graphs, what we call random and modular. And so here, all categories have an identical core structure shown in purple. And so again, each node is an individual semantic feature. And so those three purple nodes in each graph are these three high frequency important features for each category. And so every exemplar in a category has to have those three features. So core structure is identical across categories. What differs is the peripheral structure shown in blue, and I will explain that in a minute. So for our novel categories, we designed these visual stimuli, beetles and butterflies. And each consists of a base upon which any subset of 11 features can be added. So what we did for each category is to, for each participant is to randomly assign the beetle and butterfly to one of the two structures, and then randomly assign each feature to one of the graph nodes. And so I'll show you what this looks like using a butterfly example. And so in this case, a butterfly was assigned to the modular graph. So one of the butterfly features was this gray pair of wings. And so here, this feature has been assigned to this node. We also have a long antenna and pink spots. And so these are now the three core features for this butterfly category. We also have the orange wings assigned to a node in this module or cluster, along with short antenna, white arms, and toes. And then in this other module, we have twisted antenna, pink arms, a tail, and pink stripes. And we can similarly assign each beetle feature to a node in the random graph. So as I said before, the core structure is identical across these categories. So each category has those 3 core features that must exist in every exemplar from that category. What differs across categories is the peripheral structure, and specifically the extent to which each category includes additional clusters of highly tightly co-occurring features. So on the left, each exemplar from this category will have the 3 core features and then any random combination of 3 peripheral features. Whereas on the right, each exemplar will have the 3 core features and then 3 features either from one module or the other module, but never from both. So for example, no exemplar from this category could ever have both the orange wings and a tail, because these 2 features have been assigned to these different modules. And so this modular category has additional clusters of reliably co-occurring features. In previous work in the semantic domain, but also in the graph learning literature, has found that modular graphs seem to benefit learning. And specifically in the context of semantic learning, work by McClelland, Rumelhart, Rogers, and others have shown that clusters of reliably co-occurring features can help agents like neural network models learn the broader between category structure of semantic space. So we wanted to know if clusters of reliably co-occurring features within a category also benefit learning. Okay, so humans performed a missing feature task. In this task, each exemplar is supposed to have 6 features, but on each trial, participants just see an exemplar with 5 features, and they have to select which of 3 features they think is missing. And these trials were designed to test different kinds of category structure. So we could probe knowledge of category boundary, of the core structure for both the random and modular categories, and also peripheral structure for the modular category. And this task was used as both training and test. So participants learned the category structures as the task went on, and they received feedback as they went, which was how they were able to learn. And we can calculate mean accuracy for each condition at the end of the study, which is plotted here. And so participants successfully learned the category structure in all conditions. So this tells us that people are able to learn category structure on relatively short timescales. But we also found this very interesting difference between the category structures. So even though core structure was identical across the 2 categories, people found it easier to learn the core structure for the modular category. And this suggests that the overall structure of the category influences how people learned, or that the core structure specifically influenced the overall learning of that category. And this finding is interesting because it supports that hypothesis I mentioned earlier, that clusters of reliably co-occurring features can benefit learning of an individual category. So this finding is interesting in its own right, but it's also a useful difference between categories because it gives us a specific characteristic of human learning that we can now look for in different models to see what algorithms or representations within the models might reflect human learning. We replicated this modular core benefit in a second experiment. So here, this one is identical in design to the first one I told you about, but here we're just using verbal categories instead of visual categories. So this tells us that this characteristic of human learning is, it appears to be quite robust and does not depend on stimulus modality. We also replicated the modular core benefit in a third experiment with a very different design. So here, one difference is in the structures used. So here we use the same modular structure as before, but now our non-modular structure is this lattice graph rather than the random graph. And this just lets us test core and peripheral structure in both categories. So we're still comparing a modular structure to a non-modular structure, but now each participant only learns one category. Another difference is that participants are now exposed to category structure implicitly in a statistical learning paradigm. So they saw a temporal stream of stimuli. And so this time each exemplar only has 2 features, but the co-occurrence and transition probabilities of those features corresponded tightly with the assigned graph structure. And so then after that task, we asked participants to select the 3 features they thought were most important for the category they just learned about. And here is the accuracy from that task. And so And so despite the fact that course structure is identical, again, in those two categories, we again found that people find it easier to learn the course structure of the modular category. Again, revealing that the structure of the category influenced overall learning of the category. And so here now we see that the modular core benefit was replicated in 3 experiments. And so this gives us a pretty good candidate for that specific characteristic of human learning that we can now look for in different models. So we can further understand how humans learn from a mechanistic perspective. So 2 of the models that we tested were the exemplar and prototype models. And these instantiate 2 prominent cognitive theories of how people learn and represent categories. So the theory behind the exemplar model is that a category is represented as a set of observed exemplars stored in memory. So learning a new category involves storing individual traces of each exemplar that you see. And this theory is instantiated in Nosovsky's generalized context model, or GCM. And so here, we adapted the GCM to simulate our own tasks. And we find that the GCM is very successful at learning the 4 different kinds of category structure. However, it did not replicate the modular core benefit we observed in humans. And this is true across a range of values for different parameters in this model. So for example, if we tweak the parameter values to bring accuracy off of ceiling, the modular core benefit still doesn't emerge. The theory behind the prototype model is that a category is represented as the centroid of observed exemplars. So learning a new category involves integrating each exemplar's features into a single stored representation. And this theory can be instantiated as a modified GCM, which is what we did here. And so here we can see that contrasting with the exemplar model, the prototype model is not able to learn the peripheral structure for the modular category. But again, no modular core benefit is observed. We also simulated the statistical learning task with both models and found a similar pattern of results. So the exemplar model was successful at both learning the core structure and peripheral structure of both categories. And the prototype model is only able to learn the core structure. But neither model replicated the modular core benefit. So while we do see some successful learning in these models to some degree, they don't reveal the same pattern of concept structure learning that we observed in humans. And so this tells us that human learning probably relies on a kind of algorithm or representation that these models don't use. What we think is needed is a distributed representational system, like those found in neural network models. So the model we use here is a relatively simple version. The units in the input and output layers represent the individual category features. And these layers are connected by a single hidden layer. And during learning, this model develops distributed representations of both features and categories in its hidden layer. And we can observe these representations during and after learning. And we can also simulate our tasks. So here are the results of the missing feature task simulation. So similar to humans and the exemplar model, we found that the neural network model was also successful at learning category structure in the 4 different conditions. However, here we see, interestingly, that the neural network model also reveals the same specific characteristic we saw in humans. So this model also finds it easier to learn the core structure for the modular category relative to the random category, even though core structure is identical in both cases. And so this suggests that whatever representations are formed in this model might be more similar to what emerges in humans during category structure learning. And to get a sense of why this might be the case, we can look at the distributed representations within the hidden layer. And one way to do this is to look at how the representations of category features change over the course of learning. So during the missing feature task simulation, we can probe the model's representation of the features at regular intervals to see how these representations transform. And so this is an MDS plot that shows feature similarity over time. The beginning of learning is in the middle of the plot. Each dot is a different feature. And as time goes on, you can see how each feature moves through this representational space. The cool colors are the non-modular category. The warm colors are the modular category. And you can see that the feature representations from these 2 categories become dissimilar quite quickly. What you also see is that the core features from the non-modular category in blue do become dissimilar from the peripheral features in green. But this differentiation between core and peripheral features is much more substantial in the modular category. And so here the core features are in red, the peripheral features are in the orange and pink clusters. And so you can see there's greater differentiation between core and peripheral features in this case. And this gives us some insight into why a distributed representational system can support human-like category structure learning. It can learn representations of individual features, and those features become more or less similar to each other over time, such that core features in the modular category become relatively more distinct from the category's peripheral features. Lastly, we ran simulations of the statistical learning paradigm in this model. So again, we see that the model finds it easier to learn the core structure of the modular category relative to the non-modular category, replicating our observed pattern of human learning, and also strengthening the conclusion that distributed representations are an important part of category structure learning. And so in this task, the testing happened after all training was complete, but we can still look at the final feature representations in the hidden layer to see their similarity structure. So the non-modular category core features are in blue, peripheral features are in green, whereas the modular core features are in that red cluster on the right. And so again, we see that the model represents the core features as more distinct from the peripheral features in the modular category. And again, it represents the core features as more similar to each other in the modular category. And it's the distributed representations in this model that allow for these changes in feature similarity structure. So to summarize all these experiments and simulations, it appears as though a distributed representational system can explain patterns of category structure learning observed in humans. And again, these structures were feature-based structures capturing feature co-occurrences across instances of a category. So to conclude, I can now circle back to the original argument. Concepts can be represented as feature-based structures, and this structure is part of what we learn when we learn a new category. The reason why these feature-based structures are useful is because they can help explain how semantic features are flexibly activated across contexts. And these structures are learned within a distributed representational system. Thank you.